Good afternoon, everyone. Today I'm going to talk about the utilization of biomass fly ash in alkali-activated materials. My name is Xuhui Liang. I'm from CMMB Group, Microlab, TU Delft. In this presentation, I'm going to tell you what is the biomass fly ash and why we use it in alkali-activated materials and how it works. Nowadays, we are all concerning about the global warming, and the CO2 is one of the most important factors on that. And if we look at the CO2 emission in different industry sectors, we can see that, yeah, of course, the concrete account like 8% of the CO2 emission globally, but the electricity account way much higher, 28%. The reason behind is that until now, we are still using quite a lot of fossil fuels, especially the coal for the energy generation. As all over the world are taking actions to reduce the CO2 emission, so in the energy aspects, from 2015, some countries are released its coal phase-out announcements, which means by the end of the 2030, all the power plants with the coal combustion will be shut down. So you can see that the electricity from the coal combustion start to decrease from 2015, and we have more renewable energies to come. So among the wide range of the renewable energy resources, the biomass energy is very favored. It is, as you can see, that in the Netherlands, around 2/3 of the renewable energies are biomass energy. This is because the biomass is considered as the carbon neutral fuels, which means that with a good sustainable forest management, we can achieve like zero CO2 emission during the combustion of the biomass. But still, we have some byproducts that are similar to the coal combustion. We have the fly ash and the bottom ash. And from the data, you can see that the fly ash is still the dominant one. So we need to find a good solution to solve this kind of byproducts, given the fact that in the coming decades, we will have more and more power plants with the biomass combustion. So we are seeking for the possibility of using biomass fly ash to prepare alkali-activated materials. The reason is that the alkali-activated materials can be prepared with a wide range of the industry waste, containing high amounts of the aluminum silicates and calcium. And of course, the blast furnace slag and coal fly ash are still the most used precursors. And in our group, we have done research on waste glass and MSW ash. And also we can find literature that maintaining rare mass steel slag, something like that, can also be successfully used to prepare alkali-activated materials. So we are thinking if it is possible to use biomass fly ash to prepare as a precursor to prepare alkali-activated materials, especially given the fact that the coal fly ash in the Netherlands are now in quite shortage. So this is the chemical composition of the raw materials. If you compare it with the coal fly ash, that the biomass fly ash actually has lower amounts of aluminates but higher content of calcium. And also, if you see the particle size distribution, you can find that the biomass fly ash has very fine particles compared with the coal fly ash. That is due to the different ash connection methods and also the different combustion techniques. We did the Xray test to see the mineralogical composition of the raw materials. So compared with the coal fly ash, the Xray pattern of the biomass fly ash is more flat, and we can find a quite complicated mineralogical composition. The quartz, lime, hematite, and albite, microcline anhydrate inside. And for the coal fly ash, we can find the amorphous hump between 20 to 30 degrees, but not in that case for the biomass fly ash. And also we test the reactivity of the different two ashes and by the dissolve test, and we can find that we have lower amounts of the reactive silica and the aluminate in the biomass fly ash compared with the coal fly ash. And if you see the morphology of this kind of materials, actually it's also totally different from the coal fly ash. Of course, we also see some spherical particles, but the surface of the particles are mostly not smooth, but with a lot of flux. And we can see a lot of power structures, and also most of the particles are irregular in shape. And here's the mixture of the alkali-activated paste. We used 50% of slag and 50% of coal fly ash in the reference samples, and we replaced the coal fly ash with the biomass fly ash to some extent to see how it works in alkali-activated materials. So let's look at the calorimetry test results. On the left figure, you can see that with the incorporation of the biomass fly ash, the second external peak, which corresponding to the castiol formation, comes earlier with the and also with the higher intensity. This means that the biomass fly ash accelerates the reaction and makes the reaction more intensive. So to explain the reason, we also did experiments by blend the biomass fly ash with the activator and make comparison with the cold fly ash, as you can see from the right figure. And we find that around 20 hours, there's a second external peak for the biomass fly ash paste, which means that the biomass fly ash could actually react with the activator at the room temperature to form castiols, and which is also reasonable because we have a lot of calcium inside. So in the early stage, the biomass fly ash is more reactive compared with the cold fly ash, but after 96 hours, the heat flow for the biomass fly ash is lower than cold fly ash. This is because that we don't have the biomass fly ash don't have more reactive silica and aluminates compared with cold fly ash. And as for the setting time, you can see that with the incorporation of the biomass fly ash, both initial and final setting decreased. This is because that for the biomass fly ash, it contains a lot of calcium, especially lime, which will accelerate the reaction. And also the biomass fly ash contains finer particles. And if you see the morphology of it, it has more irregular particles with power structures, which also will absorb a lot of water and reduce the water-to-biomass ratio actually. But for the compressive strength, you can see that for all the mixtures, the compressive strength are comparable from 1 day to 28 days, which means that replacing cold fly ash with a biomass fly ash barely has no negative impact on the compressive strength. And we did the Xray test to see the reaction products of the pastes, and we find that the castiol, of course, are the main reaction products in all the pastes. And the lime and anhydride comes from the biomass fly ash were not detected for the B20 and B50 at 28 days, which means these kind of minerals are dissolved and participated in the reaction. And also the albite and microcline, especially for the group B50, you can see from 1 day to 28 days, the comparative intensity between these two minerals changed a little bit, which means that this kind of two minerals also dissolved to some extent and participated in a reaction. And we also did FTR analysis to see what the reaction goes. And we can find from the left figure, which is very interesting, that for the biomass fly ash, you can see that the main band is around 980. After blend with activator for 7 days, the main band shift to 952. This band is typical silicon oxide bond, which corresponding to the castiol formation. And also you can see that the band at around 680, which corresponding to the gypsum, also disappeared after 7 days blend with activator. So these two results finding also in agreement with the XRD and also calorimetry tests. And for the FTR spectrum of all paste, the main band around 950 corresponding to the silicon oxide bonds, which is also typical for the castiol formation. So now we come to our short summary. The first point is that biomass fly ash is the main byproduct in the energy industry with the biomass combustion. So given the fact that we are going to have more biomass energy plants in the coming decades, we need to find a solution to solve this kind of byproducts. And here we study the feasibility of using biomass fly ash to prepare alkali-activated materials. Here we find that biomass fly ash could accelerate reaction, and we can get a shorter setting time with a higher dosage of the biomass fly incorporation. But the biomass fly ash brings no negative impact on the compressive strength up to 28 days, which is very good. And the reactive aluminous indicates lime, anhydride, and microcline in the biomass fly ash are the main reactant components participated in the reaction. And from this research, we saw the potential of using biomass fly ash as a precursor in alkali-activated materials. But still, we need further study, like improve the reactivity of the ash, and we need to go more in details to see the reaction mechanism and also the durability related properties to get an understanding of this kind of materials. So that's the end of the presentation. Thank you very much for your attention.